Hello, welcome to today's class. In today's class, we will talk about BCD to 7 segment display decoder. We will also talk about don't care conditions and incompletely specified function before we build the logic circuit for the BCD to 7 segment display decoder. Here is a 7 segment display, how it looks like. All of you must be knowing about it, that it can be used to display the decimal digits from 0 up to 9. The 7 display have 7 LEDs and they are named A, B, C, D, E, F and Z as shown in the diagram. These LEDs can be turned on or off independent of each other, and by doing so we can display the different decimal digits from 0 up to 9. The 7 segment display also have a LED to represent the decimal point, but in our class today we will ignore the LED that is used to display decimal points. Now we can see here how the different LEDs can be turned on or off to represent different decimal digits. For example, here the LED Z is turned off and the other LEDs are turned on, and it would result in the decimal digit 0 being displayed. If we have to display 1, then only the segment B and C will be on and all other LEDs will be off. Same thing, this is how we can represent the decimal digit 2, then 4, 5, 6, 7, 8 is already represented, and then 9. So from these diagrams, you would know to display particular decimal digit which LEDs need to be on and which LEDs needs to be off. Now our task is to build a logic circuit which will take as input the decimal digit that needs to be displayed, and the logic circuit would control the 7 segment LED and then basically display the decimal digit that corresponds to the input combination. So as you can see, we have 4 inputs to this logic circuit. So we are using 4 bits because since we are representing decimal digits from 0 up to 9, so we cannot represent these 10 different digits using only 3 bits. We will need at least 4 bits to represent the inputs. And since we need to control 7 LEDs, we need to turn on or off these 7 LEDs, we need 7 outputs, 1 output for each LED. For example, here the outputs are named A, B, C, D, E, F and Z. So the A output will control the A LED. The B output will control the B LED. And when the output is 1, the corresponding LED will be on, and if the output is 0, the corresponding LED will be off. Using 4 bits to represent decimal digits is often referred to as binary coded decimal representation, BCD representation. We will have a separate class on BCD representation where we will discuss more about BCD. But what it means is that when we use 4 bits to represent decimal digits, that representation is called BCD representation. So 0 will be represented with 4 bits 0 0 0 0. 1 will be represented as 1 0 0 0 1. 9 will be represented as 1 0 0 1, and so on. Now, how to build this logic circuit? For that, we need to build the truth table first. The truth table will show the input combination and the corresponding output. And now, since we have 7 outputs, and the output section of the truth table, we have 7 columns, 1 column for each output. So output A have 1 column, output B have its own column, and so on. So each of the output has its own column at the output section of the truth table. And here we have the inputs x3, x2, x1, x0. Now, when we have 4 variables, our truth table can have 16 rows. However, only these 10 rows are the valid input combination, because our input to the logic circuit will be a decimal digit, and the decimal digit between 0 to 9. So 0 is represented as 0 0 0 0, 1 is represented as 0 0 0 1, and like that 9 is represented as 1 0 0 1. So only these are the valid input combinations, because we have decimal digits only from 0 up to 9. Now, how do we determine the values for these columns? That you have already seen. For example, when the input is 0 0 0 0, we want to display 0. And how did we display 0? We have to make Z off and all other LEDs on. So that's why A, for this row, A has to be 1, because we want LED A to be on, because we are displaying 0. So LED A should be on, B should be on, C should be on. All the LEDs should be on except Z, which should be 0. So when the input combination is 0 0 0 0, this should be the output. When the input combination is 0 0 0 1, it means we want to represent 1, and to represent 1, only B and C should be on. All other LEDs should be 0. So only B should be 1 and C should be 1. All the others should be 0. Same thing for the next row, where the input combination is 0 0 1 0, and this represents decimal digit 2. And if we have to display 2, then all LEDs should be on except F and C. So C should be 0 and F should be 0. All other LEDs should be 1. So like this, we determine the output value for each of the rows. Now, what about the remaining 6 rows? These 6 input combinations will never occur, and such inputs are actually called don't care conditions, meaning that the circuit can be designed by ignoring these conditions. So this is what we mean by don't care conditions. From this example, it may be clear that we have 16 possible input combinations for the 4 variables. We can have 16 rows in the truth table. However, out of these 16 possible combinations, only 10 of them are valid input combination. The other 6 are not valid and they will not appear as input, because we only want to display decimal digit from 0 up to 9. Now this is how we can represent the output values for these don't care conditions. So for these 6 rows, the outputs are marked as cross. It means it doesn't matter whether what the output value we consider as. It may be 0 or it may be 1. Now a function that has don't care condition is said to be incompletely specified. So here we have here we have 7 Boolean functions. One is A, the other Boolean function is B. So we have 7 Boolean functions here, and each of the Boolean function is a incompletely specified function because they have don't care conditions. Each of the output function have don't care conditions. Now don't care conditions, or don't cares for short, can be used to advantage in the design of logic circuits. Since these input valuations will never occur, the designer may assume the function value for these valuations as either 0 or 1, whichever is more useful in trying to find a minimum cost implementation. So for this input combination, we can consider the output as either 0 or 1, depending on which will benefit us in obtaining a minimized Boolean expression. This point will be clear as we discuss further. Now, when we have don't care conditions, this is how we represent the Boolean function. So the Boolean function A is a function of the variables x3, x2, x1, x0. It can be represented as the sum of minterms. You already know this notation, sum of minterms. So when it's sum of minterms, we should list those minterms for which the function is equal to 1. And as we can see, A is 1 for minterm 0, minterm 2, minterm 3, minterm 5, 6, 7, 8, 9. So for these minterms, the Boolean function A is equal to 1. Hence, we say its sum of minterms 0, 2, 3, 5, 6, 7, 8, 9. That's why we write these numbers here. And this you already know from one of the earlier class. But something new is here. Since these 6 are don't care conditions, this is how we represent the don't care conditions. So an incompletely specified function will be represented by the sum of minterms plus the set of don't care minterms. So the D is the set of don't cares. As you can see, 10, 11, 12, 13, 14, 15. These minterms are don't cares as far as the function A is concerned. Similarly, we can represent the Boolean function B as shown here. So B is the sum of minterms 0, 1, 2, 3, 4, 7, 8, 9 plus the don't cares 10, 11, 12, 13, 14, 15. So like this we can come up with this is how we can represent each of the function as the sum of minterms and a set of don't cares. Now once we have these expressions, now we can try to get the minimized Boolean expression for each of the output. So first we'll try to get the minimized Boolean expression for the Boolean function a. So here is the Boolean function, and since it is a 4-valued function, we will try to get the minimized Boolean expression using the 4-variable Carnot map. And in this Carnot map, we have already marked those minterms which are listed here. We have marked them as 1. So minterm 0 is 1, minterm 2 is 1, minterm 3 is 1, 4 is 0, 5 is 1, 6 is 1, 7 is 1, 8 is 1, and 9 is 1. So whatever minterms are listed here, those minterms I have made equal to 1. The other, then we have don't care conditions, which are 10, 11, 12, 13, 14, 15. So 10, 11, 12, 13, 14, 15. These 6 are don't care conditions, and the remaining minterms are equal to 0. So now we can, once we represent the Boolean function in a Carnot map, now we should try to make the groups of ones. So here, as you can see, we have 4 ones. So you may think that we can make a group of size 4 here. However, since we have some don't care conditions here, this would not be the correct way to group, because this would not be the most minimized expression. The advantage of having don't care conditions is that we can consider these don't care conditions as either 0 or 1. So whatever is marked as cross, I can either consider them to be 0 or 1 based on what will benefit us in getting a more minimized expression. That means based on what will help us to get a bigger group of ones. Accordingly, we can consider the cross as either 0 or 1. So here, if you consider this cross to be 1, then instead of a group of size 4, I can have a group of size 8, which will result in a more minimized expression. So when we have don't care conditions, we can do that. So we consider this cross to be 1, and hence I can make a group of size 8, and the same thing can be done for to cover these two ones. We can consider all these don't cares and 1, so that I can get a group of size 8. To cover this one, I can make a group of size 4. I cannot make a group of size 8 because this is 0. This is also 0. So I cannot make a group of size 8 this way or this way. So I have to settle for a group of size 4. And now this one is left to be covered. But if you remember, column 0, 0 and column 1, 0, they are adjacent to each other. And similarly, row 0, 0 and row 1, 0 are also adjacent to each other. So we can, to cover this one, we can come up with this group of size 4. So these 4 corner elements, since 3 of them are already 1, and this is a don't care, I can consider it as 1. So if I consider it as a 1, then I can have all the 4 corner elements as 1, and hence I can make a group of them, and this group will be of size 4. Next, that's all the ones has been covered. So now I can proceed to find the product term for each of the group. Let me show how we can compute the product term for this blue colored group. This blue colored group consists of 8 cells, and the first cell here corresponds to the min term x3 prime, x2 prime, x1, x0. The next cell corresponds to the min term x3 prime, x2, x1, x0. The next cell corresponds to the min term x3, x2, x1, x0. So on, the next cell corresponds to the min term x3, x2 prime, x1, x0. This cell corresponds to the min term x3 prime, x2 prime, x1, x0 prime. This is the min term x3 prime, x2, x1, x0 prime. This cell corresponds to the min term x3, x2, x1, x0 prime. And finally, this cell corresponds to the min term x3, x2 prime, x1, x0 prime. So now we have listed all the min terms for each of the 8 cells from the group. And now if we look at x3, it appears in the complemented form and also as the uncomplemented form. And hence we can discard this variable since it is appearing in both complemented and uncomplemented form. However, x2 also is appearing in complemented form and uncomplemented form. So we can discard x2 also. However, x1 appears only in the uncomplemented form, and x0 is appearing in both complemented and uncomplemented form. So x0 can also be discarded. So that left so only x1 is left, and hence the product term for the blue colored group is x1. I would like to mention one thing here is that when we make groups of size 2, one variable gets discarded. When we make groups of size 4, 2 variables gets discarded. And when we make groups of size 8, as you can see here, 3 variable got discarded, and we are left with only 1 in the product term, which is x1. The same thing will happen for the red colored group. I am not showing the intermediate steps, but and it's not actually required to list all the intermediate min terms. You can directly compute this product term once you are comfortable with, because as you can see, the red colored group consists of 8 cells and all the 4 rows are involved. So in this red colored group, row 00 is involved, row 01 is involved, row 11 is involved, row 10 is also involved. So definitely x1 and x0, the variables will change, and hence both will get discarded. However, this group consists of only 2 columns, and the 2 columns are 11 and 10. And if we compare which variable is changing, we see that x3 is equal to 1 here and it's also 1 here. So x3 is not changing. However, x2, which is 1 here, is changing to 0. So x2 will also get discarded, and we will be left with only x3. And since x3 is appearing as 1, it will be x3, and not, if it would have been 0, then it would have been x3 prime. But here the value of x3 is 1 in both the columns, so the product term will be x3. The same way we can find out the product term for this group. In this group consists of the 2 columns 0, 1, 1, 1, which means the variable x3, which is 0 here, is 1 here. So x3 is changing, so x3 will be discarded, whereas x2 is 1 in this column and is also 1 in this column, So x2 is not changing, and since x2 value is 1, it will appear in the uncomplemented form x2. And column wise, row wise, it consists of these two rows, 0, 1 and 1, 1. And when we look at the value 0, 1 and 1, 1, we see that x1 is changing, but x0 is not changing. X0 is 1, so it will appear as x0 in the. So x2 and x0 will be the product term. Same thing for the green colored group. The green colored group consists of column 0, 0 and 1, 0. So between these two columns, x3 is changing. x3 is 0 here, it's 1 here. So x3 will be discarded, whereas x2 is 0 here and it's also 0 here. So x2 will remain, but x2, since it is 0, it will appear as x2 prime. It's different from here. Here x2's value was 1, so hence it was x2. But here in these two columns, the value of x2 is 0, so it will appear as x2 prime. So that was about the rows, but for columns, it consists of the two columns 0, 0 and 1, 0, and hence we can see the value of x1 is 0 here and it is 1 here, so x1 will be discarded, whereas x0 is 0 in the first row and is 0 in the last row also. So x0 is not changing, so x0 will not be discarded, it will be kept. However, x0 is equal to 0, so it will be x0 prime. So like this we got the product term for each of the group. So I can now write the Boolean expression, the minimized Boolean expression, as a equal to x1, this product term x1, plus x3, this product term, plus x2 prime, x0 prime, plus x2, x0. So this will be the minimized Boolean expression for the output A. Like that we can try to get the Boolean expression for output E. The Boolean function E was sum of min terms 0 to 6, 8 and don't care conditions 10, 11, 12, 13, 14, 15. So now if we represent this Boolean function in the Carnot map, min term 0, 2, 6 and 8 will be equal to 1. 10, 11, 12, 13, 14, 15 will be don't care conditions and the remaining min terms will be 0. So again, when we have to make groups now, here we have two ones. So I can consider these two don't care conditions as 1 so that I can have a group of size 4. We already have these 4 corner elements, so we can consider this to be another group of size 4. So with these two groups I have covered all the ones. There are no more ones that are left to be covered. So we will have only two groups, and as you can see, these don't care conditions, we have considered them to be 0, and only these two don't care conditions we consider as 1. So that's the convenience of don't care conditions. We can either consider them to be 0 or 1 based on what will benefit us. So if I consider these two don't care conditions as 1, it will benefit us because I can get a bigger group which will be of size 4. Instead of just a group of size 2, I can make a group of size 4. Whereas there is no point in converting these don't care conditions to 1, because if we convert these don't care conditions to 1, then I need to make a group to cover them. So that will only increase the number of terms, it will not minimize. So some min terms, some don't care conditions we can consider as 1, whereas the other don't care conditions we can leave it as 0, depending on which will benefit us. Now once the grouping is done, we have to find out the product term for each group. We have already seen what is the product term for the green group. It is x2 prime, x0 prime. Now for the blue group, it consists of all the 4 columns. This means that the variable x3 and x2 will change and they will be discarded. However, row wise, all these 4 belongs to only one row, where x1 x0 is equal to 1 0. So whereas x3 and x2 will change, x0 and x1 will not change. For all the 4 cells, the value of x1 and x0 will be 1 0. So x1 and x0 will not be discarded, whereas x3 and x2 will be discarded. And since x1 is equal to 1, it will be x1 dot x0 is 0, so it will be x0 prime. So the product term will be x1 x0 prime. So we got the product term for each of the 2 groups. So now I can write the minimized Boolean expression as E equal to x2 prime x0 prime plus x1 x0 prime is the sum of these 2 terms. Now that we have obtained the Boolean expressions for 2 of the output, we will try to build the logic circuit only for these 2 outputs. But as an exercise, you should try to get the Boolean expression for each of the 7 output and build the complete logic circuit to convert to display a given decimal digit in the 7 segment LED. So now we'll proceed to show the implementation of these 2 Boolean expressions for output A and output E in Logisim. So here are the 2 Boolean expressions. A equal to x1 plus x3 plus x2 prime x0 prime plus x2 x0, and output E is equal to x2 prime x0 prime plus x1 x0 prime. I have already constructed the logic circuit for the 2 expressions in Logisim, and the logic circuit is here. A few new things that I would like to mention, and it is that you can get the 7 segment LED display from the input output section of Logisim. So you can click here on 7 segment LED display, and then you can place your Logisim as I have shown it to you. So here you have 4 inputs. You have 8 inputs. 1, 2, 3, 4, 5, 6, 7, 8. So these 8 inputs correspond to the 7 LEDs that we have discussed, plus 1, the decimal point. So we have total 8 inputs, 7 inputs for the 7 LEDs plus 1 input for the decimal point, and we are not using the decimal point in our class. But how to find out which input is for which LED? For that, you may look at the documentation of Logisim, and it shows that at the top, the third input is for segment A. The next input at the top is for segment B, and at the bottom the third input is for C, and this second input is for E. Sorry, this is for D. This first input is for E, and so on. So this is how you can find out which input is for which segment, or otherwise you can try to find it yourself. Let me disconnect this part just to show it to you. As you can see, if the input is now 0 0 0 0, so we are trying to display 0, right? So now if I connect this output the segment Z gets displayed, so you know that this input is for Z. If instead I connect it to the second input at the top, then this LED gets displayed. So you know that this is segment F, so this input is for F. The next input is for A, and since we are building the logic circuit for output A and E, if you look at here, we are building the logic circuit only. We are building only the partial logic circuit. We will construct a logic circuit to display A segment and the E segment. So I would connect my A output to this point, because this is the input for LED A, and similarly this is the input for LED E. Whatever logic circuit we build for output E, that has to be connected to this input of the 7 segment LED. So now when you do your exercise, you may, for example, find out the Boolean expression for output B. So then you will construct the logic circuit for that output B, and whatever is that output you will connect to the B input. Similarly, the logic circuit that you will create for output C, that you would connect to the C, whichever is the C input, you will connect to the C input of the 7 segment LED. So like that, you should build the logic circuit for all the 7 LEDs combined in just one single circuit, so that when I give the input, it shows the correct decimal digit in the 7 display. So here I am displaying only two segments, A and E. You should complete this logic circuit to control all the 7 LEDs. And how did I build? First I list down the 4 inputs, x3, x2, x1 and x0, and my expression for A is x1 plus x3, and that's why you see in this OR gate I have connected x1, I have connected x3, then the other input to the OR gate is x2 prime, x0 prime. So I need an AND gate to compute this x0. So the input to the AND gate will be x0 prime, x2 prime. So here we have the AND gate, and the input to this AND gate is x2 prime and x0 prime. And then finally we have to compute x2 and x0. So I will need one more AND gate for this, and that AND gate is here. is the AND of x2 and x0, and this output of the AND gate and the output of this AND gate also we provide as input to the OR gate. So the OR gate will, so this OR gate will compute x1 plus x3 plus x2 prime dot x0 prime plus x2 dot x0, and this output of the OR gate is our A output, which we connect to the 77 LED. Similarly, our E output is x2 prime x0 prime, that we have already obtained here. So I can take the same output here and connect it to the OR gate for output E, and the second term for output E is x1 x0 prime. So x1 x0 prime, and both we do OR, and that's the output, and this output of the OR gate is our output E, which we connect to the 7 segment LED. Now I can just do some test here. So when I'm trying to display 0, both these LEDs should be on, which is correct. If I want to display 1, both the LEDs should be off, and that's correct. I don't see this B and C is on because I have not created the logic circuit for B and C output. So you need to complete that, then only you'll see 1. And then for 2, if I want to display 2, then this also will be displayed and this also will be displayed. If I want to display 3, then only A will be displayed, E will not be displayed. For 4, none of them will be displayed, and so on. So like this you can test your logic circuit, and once you have the complete logic circuit, you will see the correct decimal digits being displayed based on what input you provide. So you complete that as part of your exercise, and actually this is all that I have for today's class. See you in the next class. Thank you. Bye.